Hi everyone and welcome to this new video. In this video we will consider a three-phase power circuit, and in this example we will consider a YY system. Why is it called YY system? The source itself is a Y configuration as shown here, so letter Y, or it's also called a star, and this is the load, and this is also in the configuration of Y or star, so this will be a YY system. So the following information is given about this YY system. The phase voltages, these are the phase voltages, are 100 phase 0 degrees, so each of the phase voltages are 100 volts, so the amplitude is 100 volts, but the phase orientation will be 120 degrees out of phase. So this will be 0 degrees, this will be 120, and this will be minus 120. So each of them has the following amplitudes and phase orientation. And we have also the loads, and these are the three, so ZA, ZB, and ZC, and they are 50 ohms each, and the phase orientation is 0 degrees. So actually we have pure resistive loads. We have the three loads here, 50 ohms each. Okay, these are the questions. What do we have? Calculate the following: the load voltages, the voltage drop across each load, the load current, so the current through each load, and the line currents, so the current through the line, actually connecting the source and the load. That's called what the line current is. So line voltages are the voltages between those two phase points. So this point A, mean B, and point A will be one of the line voltages. We will consider that shortly. And we have the last one, the phase currents. And phase currents is actually the current which is flowing or supplied by each of these phase voltages. So we have to determine that also. So let's start with the first one, the load voltages. So let's look at the load voltage. Okay, now what do we see? We have to recognize the following in this system. This is a balanced system because the loads are exactly equal to each other. That is very important because this is 50 ohms, this is 50 ohms, and this is also 50 ohms. If this is not the case, then we have the unbalanced system. So if this is a balanced system, I can consider actually that this connection, the neutral connection here, this point here, is actually virtually connected to this point. So I can consider this connection is made here because it is a balanced load. So I can say that the VA is across the impedance Z of A. So I can use that to say the following. This is the balanced load of balanced system. So that will result in the VA or ZA, because that's actually the load voltage, is equal to VA, and that is what's called what is given here is 100 phase 0 degrees. Now in a similar manner I can follow the V of ZB is equal to VB, which is equal to 100 phase 120 degrees. And the last one, this is the V of ZC is equal to V of C, which is 100 volts. Phase orient is minus 120 degrees. Now, if you look at this again, this is between the node N and node A. This is actually the voltage across ZA. This one between node A and node B is actually this voltage. So we can consider the connection here. And for the source C is between N and the C, actually this is actually the voltage across this impedance, and again they are given here and exactly the same, equal to the phase voltages. So actually this is very simple. So we have already calculated one of the unknowns. That is actually for question A. Let's move on with question B, which are the load currents. Now since we know the load voltages, this job is much easier. What can we say about the load currents? Now the current flowing through the impedance Z of A is equal to its voltage, load voltage, divided by its value. So if you use phasors here, so the voltage V of ZA is 100 0 degrees, 100 volts 0 degrees, divided by 50 ohms and also 0 degrees, which will give us 2 amps with 0 degrees phase orientation. Okay, that's actually for this one. Now for the next one, which is the current through the impedance Z of B, which is again its own voltage divided by its impedance. So that will result in 100 phase 120, because that's the different phase, and divided by exactly the same impedance. So that will give us 2 amperes with a phase of 120 degrees. That's actually for this one. Let's a little bit zoom out to see the complete picture. So I will make the last one, which will be I of ZC, which is equal to P of ZC divided by ZC, which is 100 phase of minus 120 degrees divided by 50 ohms and phase orientation of 0, and this will be 2 phase 100 minus 100 degrees. And this is actually for the last load current I of ZC. Okay, now I will continue. Let me zoom out a little bit more so I have the full picture. So I will now move to question C, because that's actually, we are actually done with question B. So line currents, that's actually very important. The line currents. The line current is actually this, so I will zoom in again. So this one, these are line current 3, this is line current 2, and this is line current 1. So line current 1 is exactly equal in this case for the load current. So I can say the following. I can say the IL1, which is the line current 1, will be equal to the load current of the impedance ZA, which is already calculated as 2 amps with 0 degrees phase orientation. If I now continue with the IL2, now if you look carefully for IL2, which is this one, which will follow in this impedance, which is exactly the same current as we calculated here. So in this case, it is also IZ of B, which is 2 amperes with the phase orientation of plus 120 degrees. And the last one, if you look also to IL3, which will be exactly equal to I of ZC, because it's in series. So we have 2 amperes minus 120 degrees phase orientation. And that's actually the 4 line currents. Let's move on to the line voltages. Those are a bit more work. So let's do question D. Line voltages. Okay, so line voltages, if I a little bit zoom out, what do you see? You see the line voltage here, that is VL1. What we have to do is we look at actually point A, and we look at actually point B, and actually we circle with the in a clockwise direction. So actually what we do is the following. So if I want to know the VL1, I need to know the voltage at point B, and I also need to know the voltage at point A. So what I do is VL1, so the load voltage VL1 will be voltage VB minus voltage VA. So it's very important to note because we are going in the clockwise direction. So what I have is the following. VL1 will be equal to, so let me move a little bit down so you can see everything. So it will be VB minus VA, and those are of course phasors. We know what VB is and we know what VA is. They're all given. So this is actually 100 volts with 120 degrees phase orientation. Let's fill it in. So it's 100 volts with 120 degrees phase orientation. The other one is voltage A. It's also given so 100 volt, and with phase orientation of 0 degrees. So how do we continue now with this? Because it is a phase notation and we are now subtracting, this is not easy with the polar notation. So what we would like to do is we convert this to the rectangular form, also this to the rectangular form, and this will allow us to calculate easily the net effect of the load voltage 1, VL1. So what I do is I use the formula to go from the polar notation to the rectangular notation. So I leave out the amplitude 100 and I do the cosine of the angle, which is 120, plus J, and I do the sine of the same angle, and this is actually for the first part. So I will move from the polar notation to the rectangular notation, or transform to the rectangular notation using this expression. In a similar form, I can use the formula and I place again the minus 100 outside the bracket, so I have cosine of 0 degrees in this case, plus J sine of 0 degrees. So if you now calculate this, so I will make this VL1, so if you now calculate this, just fill in the values for cosine of 120 degrees, etc. So what you get is, this will be minus 1 over 2, so minus in half, plus J square root of 3 divided by 2, that's actually for the first one, and then minus 100, and then 1 plus J 0. Now if you simplify this, you will have VL1 is equal to, so you add the real parts and you add the imaginary parts. So in imaginary parts only this one, a real part we will get a minus 1 here. It will be of course minus 1.5, and I will leave the 100 outside. You will get the following: 100, so minus 3 divided by 2 plus J square root of 3 divided by 2. Okay, so if you now move from the rectangular notation to the polar notation, what we do is you take, of course, you calculate the magnitude of this and the phase orientation, and that's also easily done using this familiar equation we know from the phasors and complex numbers video. So what we have is the square root of the real part squared and the imaginary part squared, and you will have the arctangent of the imaginary part, so which will be square root of 3 divided by 2 minus 3 divided by 2. So if I now simplify this and calculate everything which is shown here, I will get VL1 is 100 times, and this will be square root of 3. So this whole expression will be square root of 3, and the phase will be phase of 150 degrees. And this is actually for the expression for line voltage 1. So as you can see, you can use the formula for going from the phase voltages to the line voltage by multiplying the amplitude of the phase voltage with square root of 3. And you go with the phase for line voltage with 150 degrees in this case. So let's also do the line voltage 2 and line voltage 3, so that will give us more background and how the equations follow. So for this VL2, which will be, so let me zoom out a little bit, VL2 is, we have to of course go with in a clockwise direction, so it was VL1B minus A. Now I have to do A, because this VL2, now I have to do A minus C. That's actually the following. So I have to take the A and the C. So I will go down and continue with that expression. So that will be VA minus VC, and which is 100 phase 0 degrees minus 100 phase 120 degrees. Okay. Again, we can use exactly the same procedures we did here. So we move from the polar notation to the rectangular notation. So what you get is the following: 100 and the cosine of 0 degrees plus J sine of 0 degrees. That's for the first part. For the second part, similar expression, so you take the cosine of minus 120 degrees in this case, plus j, and then sine of minus 120 degrees. If you now calculate everything out, you will get 100, 1 plus j, 0. That's actually for the first one. And the second one is minus 100, and in the brackets I have minus 1 over 2, so minus and half, and now plus j, or I mean minus j, because it's a minus 120 degrees, so minus j square root of 3 divided by 2. Now again, if you simplify this, you will have 100 and 3 divided by 2, so 1.5, and you plus j square root of 3 divided by 2. So that's actually the addition of the real parts and an imaginary parts, and I will come up to this expression. Now again, I will move to the polar notation, which will be 100 square root of, I will take the real parts squared plus the imaginary part squared, exactly the same business we did for the load voltage of, I mean line voltage 1. So I will have the following also for the phase arctangent of the imaginary part divided by the real part. So the expression will be 100 square root of 3, and the phase will be in this case 30 degrees. So what you recognize here is actually the whole business. What you have is the following: your phase, so actually your amplitude is exactly the same, so 100 square root of 3, 100 square root of 3. So your phase voltage amplitude just is multiplied by the exactly the same numbers, so exactly the same factor, so it is 1 square root of 3. But the phase now is, if you compare this, is minus 120 degrees. So there is some, you can see some pattern here. So exactly the same expression for the amplitudes, for the line voltages, but the phase will be go down by 120 degrees. So if I now continue and do the same for the line voltage 3, I expect, so that's actually what I think, that this will also go down again by 120 degrees. So this will be minus 90 degrees. But I will do the exactly the same work for the line voltage 3, so such that we can see the procedure in more detail. So what is actually line voltage 3? So this one, this little one here, it will be of course again going from in the clockwise direction will be C minus B. So C is this one and minus B is this one. So I will go down and continue exactly the same procedure. So I will have the voltage at point C minus voltage at point B, which will be 100 volts with a phase of minus 120 degrees, and minus 100 volts and phase of 120 degrees. So again, I will have 100 and the cosine of minus 120 degrees plus j sine exactly the same phase. This for the first part. The second part, again the same formula, and we do this again because we want to move from the polar notation to the rectangle notation. For addition, we prefer to use a rectangular form. Now, if you calculate this, 100 times will be minus 1 over 2 minus j square root of 3 divided by 2 minus 100, and this will be minus a half again, and this will be plus j square root of 3 divided by 2. Okay, if you now again simplify this, so what you get is 100, and you will have minus minus, so you have a plus and half, and you have a minus half here, so that will leave us with a 0. So 0 is the real part, and the imaginary part is minus j square root of 3 divided by 2, and then I have another one, so it's actually the same imaginary part will be minus j square root of 3. And this will result in the polar notation, of course, again will be 100 and square root of 0 squared plus I will make more room for the square root. So I will have the square root of 3 squared, and the arctangent of square root of 3 divided by 0, which is of course undefined, but what we know is this will be, of course, this is a minus sign here, so be careful. So let me make this clear that this is a minus square root of 3, so this will be minus square root of 3, so that we know where it comes from. So this will be, the load voltages will be, for the line voltage, line voltage 3 will be 100 square root of 3 phase minus 90 degrees. And that's actually for the line voltage 3. And what you recognize, as we expected, the phase is again reduced by 120 degrees. That's very interesting. So we already know this for the line voltages. Okay, let's move on. What is the following? So we have a line voltages. We have actually question D also calculated. Let's move on to phase voltages, phase currents. Phase currents. I already explained this in the beginning. These are the currents actually flowing through the phase voltages. So I have the phase current here. This is the phase current. So if I make use a red color, that this is actually the phase current. So this is actually IP phase for the C, this is the IP for A, and this will be IP for B. And what you recognize directly is this one is exactly the same as IL1, and this one is exactly the same as IL3, and this one is exactly the same as IL2. So we have actually calculated that here line current. So what we can say, this is actually the last one, and then the whole business in this example is done. So we can say the following: phase currents so I have the following: IP of A, which will be IL1, which is 2 amperes 0 phase orientation. IP of B, so the phase current for the voltage VB, will be IL2, which is 2 amperes phase orientation of 120 degrees, and last one is the phase for the voltage source VC is IL3, which will be 2 amperes with a phase orientation of minus 120 degrees, and this will be for the phase currents, and actually the whole business. So let's look at it again by zooming out. We have a complete picture. So we have is the phase current finally, and we have used the line currents here to calculate that, and it's actually the whole business for the last one. Again, this is a YY system. This is actually the first example in this series about three-phase power circuits. And remember, we can use, of course, the formulas which are actually given here for square root of 3 times the amplitude of the phase voltage, but I've used this formula to explain why this formula is used here and what's actually the square root of 3. So that's actually very important to recognize that instead of using that blindly. Okay, thank you very much, and I will see you in example 2 with a different system and different configuration for this power system, for this three-phase power system. Thank you very much, and see you next time.